Now in this chapter we will study something unique. It is called torque or moment. Now in previous chapters we were studying forces acting on a particle. Now imagine if a force is not acting on a particle but at some distance from a particle. Now this would result in a tendency of rotation, which is called moment. So this chapter is divided into 5 sections. In section 1, we're going to discuss moment of a force in terms of scalar. And before going to discuss moment of a force in terms of vector, we will go through a cross product. And in next section, we will discuss principles of moments. And in the last section, we will discuss couple. Now, what is a moment? Now, when a force is applied to a body, it will produce a tendency for a body to rotate about a point that is not on the line of action of force. Now, this tendency to rotate is sometimes called torque, but most often it's called moment of force or simply moment. So, what I mean is that moment is actually nothing but a tendency to rotate, and it's also called torque or moment of a force. Now, for example, imagine this wrench, and a guy is using this wrench to unscrew a bolt. Now, how he will unscrew a bolt? He will apply a force which is actually perpendicular to the line of action of force. So this is a line of action of force, and the distance has to be perpendicular to the line of action of force. Now you can imagine by applying a force further from a point of particle, then it will add some rotation, and this rotation will help to unscrew this bolt. Now this rotation is called moment. Now, in order to quantify how much is the moment, we need to define its magnitude. Now the magnitude of a moment can be defined as that it is directly proportional to the magnitude of force and perpendicular distance of moment arm. So if you look at how we mathematically quantify the magnitude, so it says that magnitude is directly proportional to the magnitude of force and perpendicular distance or moment arm d. So what it would mean is that the higher the applied force, if you will increase the force, then you will increase the rotation, that is the moment. And secondly, imagine if you increase this distance d. For example, if you're using a bigger wrench and then you're applying a force at a further distance, which is twice the distance mentioned here. So you can imagine that the amount of rotation produced will increase. So it means that if you increase a d or if you increase force, you will increase this rotation or a tendency to rotate, which is called moment. Now moment also have a direction because it is a vector quantity. So a direction is defined by its moment axis. Now what is a moment axis? Moment axis is a perpendicular to plane that contains force F and its moment arm d. So basically we were discussing right hand rule in previous chapters. Now we can use this right hand rule to calculate the direction of moment. So this is a moment axis because along this axis there is a tendency to rotate if we apply a force in this direction. So this axis is called moment axis, and moment axis is actually perpendicular to the plane of action of force and moment arm d. So for example, this I'm looking this from the top. So this is a bolt which is rotating along this direction. And why it's rotating along this direction? Because we are applying a force in this direction. And this is basically a distance d between the line of action of force and the axis of rotation. So this is actually a plane because the distance also and the force F also is acting on the same plane. So if that's the situation, then if you see a direction pointing upward from the plane or downward, so this is the direction of moment. And we'll go into detail about the direction concept. But for now, you can try to understand that if a force and distance are on the same plane, then the moment axis would be perpendicular to that plane. Okay, so what if we have multiple moments acting on the same plane? So we can find the resultant moment if you have like one, or because previously we studied only one force acting on it. So now imagine you have same point and you have three different forces acting on that plane. So you will have three different moments. I represent these three different moments with M1, M2, and M3. And all these moments have different perpendicular distances d. So resultant moment says that for a two-dimensional problem, so basically it's a two-dimensional problem, that is all the moments are on the same plane. So the resultant moment can be determined by finding the algebraic sum of those moments. So basically what it's saying is that if you want to calculate the resultant moment, so basically you will just add all those moments and you can get the resultant moment. So for example, and by convention, we take a moment acting anti-clockwise as positive. So if a moment is clockwise, we will take it as a negative, and if a moment is anti-clockwise, we will consider that moment as positive. So in order to figure out the positive moment resultant about axis O, this is axis O. So what we can do is that we can sum all the moments, and a moment is actually nothing but force into distance. So we have force 1, and force 1 has a perpendicular distance d1. We have force 2, it has perpendicular distance d2. We have force 3, it has perpendicular distance d3. So that's how you can calculate the resultant moment. Now let us do one example and it will be more clear how we can calculate the resultant moment. So there are four forces, 1, 2, 3, 4. So you have one force which is 50 Newton, another force which is 60 Newton, another force you have 20 Newton, another force you have 40 Newton. And what we are interested in this example is to calculate the resultant moment of four forces at point O. So as we know that anti-clockwise moment positive at point O would be equal to sum of all the forces. Now that's how we will calculate moment of all forces. Now how many forces are there? We have four forces, right? So the first force is 50, and this force has a distance of 2 meters. And this force is gonna rotate, a tendency to rotate at point O is clockwise. So if, for example, this is a point O and this is the force, right? 50 Newton, and the distance between them is 2 meters. So the tendency of rotation is in this direction, right? So 50 Newton is directed point downward, and it will rotate the point O clockwise. So clockwise, we have considered the notation anti-clockwise as positive, so clockwise would be negative. So since this moment is clockwise, so we'll put negative, and the force is 50 Newton, and the distance between them d is 2 meters. So now we have considered this force. Now let's consider this force. Now this force is 60 Newton, and what is the distance d? We know that if this is point O and this is the force acting, so first we draw the line of action of force, and then we calculate the distance between the axis and line of action of force. Now in this case, we have a point O here, and we have a force here, 60 Newton. So what is the line of action of force? This is the line of action of force. Now the distance between the line of action of force and from axis O to line of action of force is basically 0. Now let's move towards 20 and 40 kilonewton. Now how to calculate 40 and 20 kilonewton distances. Now I'm gonna draw this here. We have point O, and this is 4 meter, and this is 3 meter, right? And this is the force. Now what we have to do is that we have to draw the line of action of force, and then we have to calculate the distance from line of action of force and the axis O. So we are interested in this distance for 20 Newton force. So what is this distance? This distance is basically this distance. Now what do we know? We know this is 30 degrees. So we are interested in finding out this distance. So this distance can be found because this is 30 degrees. So in order to find the opposite to 30 degree, we can use sine of 30 degree multiply by 3. So this would give us this distance. So now I can continue adding in this equation, which is summation of moment at O is equal to, now let us add 20 Newton force. So 20 Newton force is gonna apply an anti-clockwise moment on O. So it's positive 20, and what is the distance? Distance is 3 multiplied by sine of 30 degree. Now let's move to 40. Now a 40 Newton force will apply a positive clockwise moment. So clockwise moment is negative 40 Newton into, now how to calculate the distance D? This is, I'm gonna draw again, this is O, this is 4 meter, and this distance can be calculated by using the formula 3 cos 30 degree. As we have discussed by how we can resolve the forces into its components, we can also resolve distances into its components. So the total distance, because this is the force and this is the line of action, so we are interested in this distance. So this distance would be equal to 4 plus 3 cos of 30 degree. So 40 into 4 plus 3 cos of 30 degrees. So if you do the math, you will get total moments equal to negative 334 Newton meter. Now we are getting result in negative. So it means that it is a clockwise moment. It is not anti-clockwise moment. So we assume it was anti-clockwise, but the answer came out to be negative. It means that this is a clockwise moment. Okay, so that's how you resolve different forces, and that's how by using different forces you can calculate the total resultant moment. Okay, so before going into a moment vector notation system, let's just discuss cross product. Now what is a cross product? A cross product is also, just like dot product, is a method of multiplying two vectors. But if you do a cross product between two vectors, that will produce a vector perpendicular to both vectors. So we'll understand why we need cross product when we'll go to the next section. But mathematically, the cross product of two vectors will yield a third vector which is perpendicular to both vectors, and mathematically we can write this as capital letters and bold. Bold would indicate that it is a vector, and if it's not bold, then it indicates that it is a magnitude of that vector. And we also need some kind of direction notation to point out a direction, because a vector also have a magnitude and also it has a direction. Now let us try to find what would be the magnitude of resultant by multiplying two vectors. So if we multiply two vectors, how we can calculate the magnitude of these resulting. So this C is actually a vector magnitude. So I have written this in non-bold form, which represents magnitude. So the product of magnitudes of A and B, so if you calculate the magnitude of original vector A, original vector B, and you multiply this by sine of angle between them, then this would give you the resultant magnitude of two vectors. So for example, you have vector A, you have vector B, you have a theta between them. So if you get the magnitude of vector A, get the magnitude of vector B, and you multiply AB with sine of theta, then you will get the magnitude of vector C. So you will get another vector C, and that vector C has a magnitude AB sine theta. Now, how to find the direction? Now, we have studied this right hand rule in previous lectures. So vector C has a direction, and that direction is perpendicular to the plane that contain A and B. So this is, let's just say this is a plane. This is vector A. This is vector B. Now, if you multiply that vector A and B using cross product, then you will get a third vector, but the third vector would not be in that plane, would be perpendicular to the plane. So either it would be directing out of the plane or into the plane, but it would be not in the plane. It would be at a perpendicular distance to the plane that contain A and B. Now, this is a vector C, which we were talking before, and the vector C is a cross product of vector A and B. Now, the magnitude of that vector is AB sine theta. But since it's a vector, we also need a direction. Now that direction is calculated by using right hand rule. So if this is vector A, so this was a 2D figure, now this one is 3D figure to better illustrate where would be the direction. So let's just say this is a plane. This is x-axis, this is y-axis, and let's just say this is out of plane, z-axis. So it would be a kind of 3D. So vector A and vector B are on x-axis and y-axis, but the vector resultant vector will have a direction in the third axis, which is perpendicular to these two axes. So that's how you calculate the direction of a cross product. So this AB sine theta is a scalar which defines the magnitude, and this unit vector mu c, which we added, defines the direction, and that's how we calculate the direction by using right hand rule. Now, similar to the dot product, we also have these three laws of operation: commutative law, associative law or multiplication law, or distributive law. So commutative law is not valid in the case of cross products. So remember, in dot product, A dot B was equal to B dot A, but if we are taking cross product, then A cross B is not equal to B cross A because it changes the direction. Now, what is associative law? Associative law is simple, and it's also used in cross product as well. For example, you have A cross B vector and you want to multiply this by some scalar, let's just say it's alpha. So you can do this. You can either multiply that A with vector A and then you can do the cross product with B, or you can also multiply that scalar with a vector B and then do a cross product with vector A. The result would be similar. The distributive law says that if you have two vectors which you're gonna add together and then you will take cross product, you can also do two cross products like this, and then you can add these two vectors and you will get the same results. So in cross product, the commutative law is not applicable, but associative law and distributive law is still applicable. Now let us discuss a vector formulation. So remember, Cartesian vector formulation included these vectors I, j, k, and we're going to use these to get the sense of directions in case of cross product. Okay, so we all know that along x-axis you can represent this in the form of Cartesian vector by the symbol I. Along y-axis you can put j, along z-axis you can put k vector. Now, if in the case of cross product, if two vectors are multiplying and two vectors are on different dimensions, axes, for example, you have two axes, x-axis and y-axis, and in x-axis you can represent it by I, in y-axis you can represent it by j. So if two vectors are multiplying on x and y-axis, for example this vector and this vector, so the resultant would also include these Cartesian vectors multiplication. So you will, by multiplying by I into j, you will get another vector called k, and that would represent the direction. So you can also understand, like, by multiplying which two axes will get which one by understanding this figure. So you have I, j, k representing three axes, and if the direction of I, j, k is positive if it's anti-clockwise, and the direction would be negative if it's clockwise. Now, what do I mean by that? So let's say we have I cross j. So if we are multiplying I with j, so we are going from I to j, and this is a anti-clockwise direction. So it means we have a positive third axis, k, because if you multiply two vectors, the resultant vector would be perpendicular, so it would be on another axis. So if you are multiplying k vector with j vector, so resultant would be on I direction. So if you are multiplying I with k, the resultant would be on j direction. But all we need to understand is that is it positive or negative. So for example, in the case of, let's just say in the case of k and I, so from k you are going to I, from k you are going to I, and this is also a anti-clockwise direction. So anti-clockwise direction is always positive. So k multiplied by I would be obviously ki, so it would be j, but the direction would be positive because it's anti-clockwise. So let's take an example of a clockwise direction. So let's say we are multiplying I with k. So if we multiply I with k, so from I you're going to k. So it is a clockwise direction. So in clockwise direction you will put minus, and it's I and j, so resultant would be k. Now, what about if you multiply I vector with I vector? So if you multiply I vector with I vector, you will get 0. And the reason between is that both the vectors I and I has sign of 0. So sign 0 is 0. Okay, so crossing two unit vectors in a clockwise fashion around the circle yields positive, as we have discussed here. If it's clockwise, counterclockwise, then it will result in a positive unit vector. But if it's clockwise, then it will get negative. So this is just some terminologies which is important if you know, because later you can also convert this into a matrix form, which will do it right now by multiplying two vectors. So let's just say I have a vector A and a vector B. Now vectors can be represented in terms of Cartesian vector formulations, as we have discussed in previous lectures. So A can be represented as AX plus AY plus AZ. B can be represented as BX plus BY plus BZ. And it's in x-axis, so it would be I, in y-axis, and in z-axis, x-axis, y-axis, z-axis. Now what is cross product? In cross product we do the cross product of two vectors. Now we're going to do the cross product of these two vectors. So if we'll do the cross product, we will get this result. So let's discuss how we got this. So basically we have to multiply, uh, not multiply, basically we have to do the cross product of two vectors. Now how to do the cross product? Now if we are going to do the cross product of these two vectors, we have to do the this we have to multiply this with this and this. So AXI would be multiplied with this BXI plus AXI would be multiplied with BYI, and again AXI would be multiplied by BZK. Now after this you will go to this and then you will do the same procedure, and you will move to this and you will do the same procedure like shown here. First AXI was multiplied with BXI, and then we got this, then it was multiplied by BYJ, we got this, it was multiplied by BZK, we got this, and then we move to AYJ. In AYJ we again multiplied by this, we get this, AYJ multiplied by this, we get this, AYJ was multiplied by this and we got this. And in the last we do this for AZK as well. Now we have seen that I dot I was equal to 0, so we'll cancel this out. J dot J was 0, we'll cancel this out. K dot K was 0, we'll cancel this out as well. Now we have these three. So if we multiply I by J, what we will get? If you multiply I by J, you will get K. So instead of I by J, you can put K. Instead of I by into K, you can put negative J. Similarly, you will do with all these and you will get this final equation. We can also write all this, instead of doing multiplication and instead of doing the cross product of different units, we can just write it down in terms of this matrix. So if you have studied matrix, you can easily write it down in the form of matrix. So on the first you will put I, J, K, and then you will just put the component of A, which is AX, AY, AZ, and then you will put the component of second vector, which is BX, BY, BZ. And if you resolve this matrix into its components, then you will get similar results. And we'll also do this. So let's try to resolve these matrix into the components to get the same results which we were getting before. So if you have studied matrices, so basically it's a determinant of a matrix. This is AX, this is AY, this is AZ, this is BX, BY, BZ. So in order to determine the determinant of matrix, and this matrix is 3 by 3, it means that it has 3 rows and 3 columns. So how to determine this determinant? So the method is, first you put I outside, and then you convert 3 by 3 matrix into 2 by 2 matrix. So you put this thing here. So it would be AY, AZ, BY, BZ. Then you put minus, then you put J, and then you put this thing and this thing. So it would be AX, BX, AZ, BZ. Then you put third, and then you put this 2 by 2 matrix here, AX, AY, BX, BY. So I'm not going into the details because this would be out of the scope of this lecture. But if you know a 3 by 3 matrix, and if you want to make the determinant of these matrix, so that's how you do. And I'm just gonna solve for this one because this can be solved. You have to multiply this with this and you have to put negative and multiply this by this. So it would be ay bz minus az into by. Similarly, you will do for j and you will do by k. So you can see you get I ay bz minus az by. And similarly, you can also, if you do the determinant for this, you will get this and this. So that's how you can solve, you can calculate the cross product of two vectors by formulating a determinant of a matrix. So these are some of the methods I went, and you can also use these methods to calculate the cross product. Now we have understand the cross product. Now let us try to formulate the moment in terms of force vector. Before we were doing force scalar, now let's gonna do force vector. Now, what is the moment of a force? The moment of a force can also be expressed by using a vector cross product. Now this is different than a scalar, and we'll discuss how it's different. So mathematically you can write the moment as a cross product of the resultant force F and a force F. Before we were using a force and multiplying with the distance d, which was perpendicular distance between the line of action of force and the axis of rotation. So this is a moment for force scalar. Now we are trying to express this by using vector quantities. So in vector quantities, instead of using distance, we can use position. Now position is a vector. So before we were using d, now we're going to use r. So r is a position vector. So we have two vectors, and we can calculate the moment by multiplying these two vectors, which is vector r and vector f. So what is r? R is a position vector directed from O to any point on a line of action of force. Now we can calculate the magnitude of these two forces by this formula, which we have studied before, which is A cross B was AB sine of theta. That was the magnitude. So this is the magnitude, and we can see that if we resolve this into r sine theta, so we can see this r sine theta is nothing but d. So r cross f is equal to fd if we want to do the moment of a force scalar. But we are doing force vectors, so we also need something called direction. So the direction can be calculated by using right hand rule, and we have also done this in the previous slides, where you have one vector here, you have another vector. So this is a first vector, and this is another position vector. So the moment magnitude can be determined by using rf sine theta, and the direction can be determined by using right hand rule. So this would be the direction moment, which is a moment axis represented by this. So I hope this is little bit clear, but let's do one example to make it more clear. So this is example, and what we have to do is that we have to determine the moment produced by a force F at point O. So this is a force, and what we are interested in is to find the moment at point O. So now this is a little bit of complicated problem, because this is a three-dimensional problem. So you have x-axis here, this one, you have y-axis here, and then you have z-axis here. So what we can do is that we can also try to solve this by using a Cartesian vector system. So but before, what is a force? I have trying to put this in the bold form. So this is a force vector. Now force vector is nothing but a vector with a direction AB. So I am trying to calculate the force. So what would be the direction? So because we also need the direction. So direction is a force vector divided by its magnitude. This would give you the direction. So let us try to find the direction first. So what would be the direction? So direction of AB, I'm trying to find the direction of this force, UAB. So UAB is first a vector. So what is a vector? So this is a resultant force F, which is 2 kilonewton, but this is the resultant force. We have to use this force and convert it into the Cartesian vector form. So in order to convert this into Cartesian vector form, we have to multiply this force with UAB. So let's try to find UAB first. So UAB would be equal to a vector which is 4i plus 12j minus 12k. Now how I am getting all this is the 4 which is along x-axis, so 4i. This is 12 which is along y-axis, so 12j, and this is 12 but it's in downward, so I will put negative 12k. So how to calculate the magnitude? Magnitude we can calculate by squaring all these distances and making the square root of it. So this is how you calculate this UAB. And if you multiply this, if you use this equation, so you will multiply this force, which is 2 kilonewton, with everything this. So I'm going to solve this. If I will solve this and multiply with this 2 kilonewton, then I will get the force 0.4588i plus 1.376j minus 1.376k kilonewton. So now what we have done is that we have resolved this 2 kilonewton force into these three directions. Now in order to do the cross product, we can do the cross product if we want to find the moment. So we can just do the cross product of resultant vector r with the force F. So what is a resultant vector if we want to calculate this RA? So RA would be IJK. Let's just put this first. Now what is RA? RA, because we have to calculate the moment from at point O. So if you look closely, you have two moments that are being produced. One is along this direction, one is along this direction, and there's another one along the y-axis, but that's zero because z-axis, and that's zero because the force is passing through the line of action of force. So just this example is just to give you a rough understanding of how you can calculate the forces, and I'm not going into the details, but if you calculate RA, you will get 0.0012, and we have already calculated the force, which is 0.588 and 1.376 and minus 1.376. So if you do the math, you can calculate the resultant force by using the method which we have discussed previously. So this is roughly how you can calculate the moment if you have a three-dimensional space and you have a force acting somewhere, and then you have to resolve the forces into its components, and then you can also resolve the distances into its components, and then you can use this matrix determinant and can calculate the moment. So this, now the next section is about principles of moment. So what is the principle of moments? So before we have calculated the resultant moment if you have a force, but that is not usually what we do. We have a simpler method. So Wagon's theorem is also called the principle of moments, and what it says is that moment of a force about a point O is equal to sum of moments of components of a force. So the example which we have done previously, we don't need to do it this way. We have an easier way, that is, first we resolve the forces into its components, and then we can use these components to calculate the moments. So in this way it would become easier to calculate the moments, and we will discuss this in the upcoming chapters where we'll discuss internal forces. So we'll also calculate moments, and that's the nice way to calculate moments. But for the example, for the case of here, we can just think, for example, if this is the force, we calculated force a moment by using previous method, but we can also do it in a simpler way. That is, we can resolve these forces into its components, and then we don't have to do the distance formulations. So we can just directly, then the line of action and distance between them become easier in this case. But we will do this in coming chapters. So for example, you have force F, and this is the line of action of force, right? So it gets a bit complicated to calculate the moment. But if we resolve these forces into x and y axis, then we already know the axis, so we can just calculate. So it gets easier to calculate the line of distances. So it gets easier to calculate the line of action of force and distance between the line of action of force and the axis of rotation. And we'll do some couple of examples later in the lecture series. Now, what is a moment of a couple? Now, couple is also a very interesting phenomena, and a couple can be defined as two parallel forces that have the same magnitude but opposite direction, and they are separated by a perpendicular distance between them. So for example, if you are driving a car, you have a wheel, and what you usually do is that you put hands on the wheel and you drive with both of the hands. So what you are doing is that you're not applying one force, and with the help of one force you're not applying a moment. You have two forces, and with the help of two forces you are trying to rotate the wheel. So this mechanism is called couple, in which you have two forces, one in this direction, one is another direction, and you have a distance between these two forces. So the moment produced by a couple is called couple moment. Now, there are two formulations, scalar formulations for the couple also, and vector formulation. Now, scalar formulation is pretty straightforward. The formula is F into D, just like before. And where F is the magnitude of one of the forces and D is the perpendicular distance or the moment arm. So this is a moment arm or perpendicular distance between these forces. In vector formulation would be also somewhat similar. The formula for vector formulation is R cross F, and that would equal to RF sine theta, and which can also be converted into scalar formulation like we have seen before. So this is chapter 4, and see you in the next chapter.